When we are dealing with multiple classes instead of just two, we need to scale up the entropy from binary cross-entropy to cross-entropy loss. And in this case, we use the instead of the sigmoid, we use the softmax function. And here we have the numerically stable softmax function. We subtract from the raw model output, or from the logit, the maximum value from this output. And we normalize values by this way, and then compute the exponent from these values, just to make the result more stable, yeah? In case if we have very high values in the logits, our exponent just gonna be very high value, yeah, it's just explode at some point. And to prevent such behavior, we subtract from the logits the maximum value. And the softmax function derivative forms a Jacobian matrix like this, and it's not that easy to compute, but the cross-entropy loss and its gradient after softmax is simply softmax minus the y. It's very easy to compute compared to the Jacobian matrix. Just because of this unique property, most of the time cross-entropy implements with the softmax. You can see the same implementation in the PyTorch of the cross-entropy and the softmax, just because the backward pass is very easy to compute. But let's implement cross-entropy step by step. Let's copy our BinaryCrossEntropy class and use just the CrossEntropy class. And we have the same epsilon, I think the same reduction, it's totally okay. And then for the compute loss, we need to change the computation. Let's by default install this to none. And what we need to do, we need to compute first of all this shifted prediction. Let's create the shifted pred, and we subtract from the prediction dot max. So it's exactly what we need, yeah. And then we need to compute the expected values. It's just the exponent of the shifted prediction. And then let's create the probabilities variable, and we know that we need to compute the exponent values over the sum of the exponent values dot sum along the last axis -1, keep dimensions true. And because we have the division, we need to add the epsilon term in case of 0, yeah. Just all the time when we have the division, we need to add this tiny value to prevent any possibility to divide by 0. Okay, and now we are ready to compute the loss. And here is our formula for the cross-entropy. Okay, we need to add this negative sign, then we multiply this yi, it's the target value. We need to multiply the target times, we have the log probabilities, so it means that we compute the probabilities dot log. Yeah, but the only thing that probably we need to add is just we need to add here the self dot epsilon, just to prevent the 0 case, yeah, because for the 0 log just returns the negative infinity, and it's absolutely inappropriate, yeah. And it's something similar with the division, yeah, we always need to add tiny value before we call the log for the numerical stability. Okay, and we multiply target by the log probabilities, and then we sum, because we have this sum notation, along the axis -1. And I think that this is exactly what we need. We have this log probabilities term. We have target multiplies by the log probabilities, and we sum along the last axis in our tensor and return the loss. And I think that this is exactly what we need. But there is another way. The log-sum-exp function is defined as you can see on the screen. We compute the exponent of every term inside z and sum them up and compute the log from this sum of the exponents. And this function it calls log-sum-exponent. For numerical stability, it can be defined like this. We have this zj minus maximum value from this vector z to shift all the terms inside the vector in the direction of 0, because in this case, if we compute the exponent just for the pure z term, it can be very large result. And if we subtract the maximum value, shift towards the 0 all the items in the vector z and compute the exponent, it adds some numerical stability to the result. Then we compute the log from the sum and add the maximum value of z to prevent any possible zero case scenarios, or negative scenarios for the log function, because it can be some negative values from this log, because log defined mostly in the negative diapason, and in case if we add the max, we just shift towards the positive values. Now let's recheck the definition of the softmax function. It's at the exact point we compute in the numerator the exponent of z at the point I over the sum of all of the terms from the vector z, and we use the exponent function for every of the term and sum them up. So if we take the log from both sides, you can see the result, because we can apply the log rules, when we have the division inside the log body, we can we can replace this division to the subtraction of log of the numerator and log of the denominator, and it means that we leave only the zi term, because the natural logarithm of e to the zi power equals to the zi minus the log of the sum of all of the exponents term. And this is exactly the key equation that used in the log-sum-exp version. It's right over here. So instead of computing softmax first, then taking the log, we directly compute the log softmax in one step with this log-sum-exp function. But the only thing that we need to do in this case, we need to implement the log-sum-exp inside the tensor class. We can define this as the additional method inside the class. Let's define the method log-sum-exp right under the formulas. Then we move this method inside the tensor class, but right now I wanted to use this formulas as a hint, to make the implementation step by step. As the first argument we have self, then we have axis as the optional, and we need to make a union of the integer and tuple of the integers, because it can be one integer or bunch of integers that we use as the axis. By default, let's use none. Okay, and the last parameter is keep dimensions. Keep dimensions as the boolean, and let's use false by default. And we return back the tensor Okay, and first we need to compute the maximum value from the self. Let's define x max, because we use x maximum all the time, yeah, here and here, when we subtract from the z and when we add to the log sum term. Okay, and we need to compute self dot max. So as the second step, let's use the shifted exp. We know that we need to subtract from the self, we need to subtract the x max, and then we need to compute the exponent. This shifted exponent, it's right over here, yeah, it's this term inside the sum. And we know that the next step is to compute the sum exponent, yeah, we need to sum the exponent up. Okay, let's compute the sum exponent term, and we need to run the shifted exponent dot sum, but we need to provide access in this case, and also we use the keep dimensions term directly inside the sum. And now we have the shifted exponent, we have the x maximum term, and we need to compute this numerically stable log sum exponent. We need to first of all just let's define the variable log sum exp, and it equals, so we know that we need to use the max of our input, yeah, of our z, let's say logits, yeah, or whatever. In this case it's right over here, but we need to call the squeeze to be absolutely sure that there is no any potential troubles, yeah, squeeze along the specified axis. And we need to add to this maximum sum exponent, it's right over here, yes, sum exponent, and we need to compute the log from the sum exponent. And I hope this is the exact implementation and we follow the same rules as described right over here in the numerically stable version of the log sum exponent. Last step, we need to return back the tensor. We need to put this log sum exp, then requires gradient equals self dot requires gradient. Now let's copy this implementation and put it right over here under the mean, yeah. So and now it works fine, yeah, all the functions defined inside the tensor class. Right now we have the definition of the self. Just because we are using existing operations like max, exp, sum, squeeze, log. Since these functions already have their backward steps implemented inside, for example, for the log we have this backward, yeah, and we have this dependencies list that we prepared inside the operation. We don't need to manually define backpropagation for the log sum exponent. When we during the backward pass, each operation computes its gradient step by step, propagating derivatives automatically. And I think that this implementation looks fine. So right now we can move to the cross-entropy and implement the cross-entropy with the log-sum-exp. And let's recall the definition of the cross-entropy, yeah? And cross-entropy, it's the target values, yeah, in our case is yi in the formula, times the logarithm of the probabilities. And we convert the logits to the probabilities with the softmax. And it means that we can use, instead of the log probability, the log of the softmax. And as far as I remember, we just applied the logarithm rules, yeah, and based on the logarithm rules, we can convert this logarithm of the softmax to the logits minus the log sum of the exponent of the logits. In our case, we can use the logits minus the log-sum-exp of the logits. So we can implement it easily using the log-sum exponent. Yeah, let's replace this probabilities. We can replace them with the predicted, yeah, because the predicted it's our logits minus the predicted, and you can see we need to call the log-sum-exp along the axis -1, and we need to use keep dimensions true, yeah, because we need to preserve the dimensionality of the logits, yeah, and we convert by this way to the log prop. So we need to replace these probabilities to the log prop. And this is exactly what we need. We use the log probabilities, yeah, and right now the only thing that we need to do is to drop this log and exponent, and we use just the target times the log prop, yeah, and then we compute the sum along the axis -1. In this case, we return the pure loss result, yeah. So I think that this is the exact implementation that we need, yeah. It's pretty straightforward. We use this log-sum exponent function from the tensor that we already implemented before, and it looks pretty simple.